Welcome back. Today we're just going to start off light and talk about input and output values. Okay, so in our toolbox, so we discussed lightly in the last unit at the end the difference between a relation and a function, and we're going to kind of broaden that a little bit with adding in domain and range. Some of these terms will probably look familiar to you guys. So let's review. A function is what? A function is a set of numbers. Oh no, not just numbers. What kind of numbers? Well, it's a set of ordered pairs. So a set of ordered pairs, and this is the important part, where each x has exactly one y. That's key. Okay, now we discussed a couple terms that go along with our x and y values. So our x values, let's see what you remember. Our x values are inputs, and our y values, those are the outputs. So the x values, so in an equation or in a function, we have an independent variable and a dependent variable. So the y values depend on the x values. So the y values are our dependent, and our x values are the independent. There's also another one. So x values, they're inputs, they're independents, and that's how I remember them. There's also another word, and it is the domain. So the x values are the domain of a function, and the y values are the range, domain and range. So 3 terms, all representing x values, 3 terms, all representing y values. So we're given a couple scenarios, and it says identify the dependent and independent variables in the following scenarios. Okay, so it's that time of year again, and you're buying Girl Scout cookies. Awesome. The cookies are $4 a box, so it wants us to write an equation describing the amount you spend on cookies. Okay, so information, what are we given? Girl Scout cookies, cool beans. Cookies are $4 a box. So write an equation describing the amount that we spend on cookies. Okay, so what are cookies? $4 a box. So how do we represent $4 a box? 4B, $4 a box. And $4 a box tells us what? Tells us the amount that we're spending. So that equals A. Quick and easy. Now look here, it says represent the situation using function notation. So this is an equation, A equals 4B. Now before we can write this function in function notation, we need to come back up here because they asked us identify the dependent and independent variables. So does the amount depend on the number of boxes, or the number of boxes depend on the amount? Well, the amount we spend, that's definitely going to depend on, well, how many boxes of cookies. So since it depends on the boxes is our independent, and the amount that we're spending is the dependent, because, well, it depends on how many boxes. When you're writing this in function notation, it's A of, because amount is our dependent, and the dependent depends on what? The boxes. So it's A of B. So the amount that we spend depending on the number of boxes equals 4 times the number of boxes. Okay? So the only difference between writing an equation and then writing it in function notation is that dependent, it's A of, and then whatever is representing our x in that case. That's literally the only difference. So you're still writing the equation using your same Ideas? Principles? I don't know. So your grandma always keeps a jar of candy on her counter. Every time you visit, she lets you choose 3 pieces of candy. So write a function representing the amount of candy left in the jar if there are 100 pieces to begin with. All right, mark that text. What's important? Well, keeps jar on the counter. That's pretty important, but not going to help us write an equation. Every time we visit, okay, she lets us choose 3 pieces of candy. So we are writing a function. Cool beans. Write a function representing the amount of candy left in the jar if there are, that's also important, 100 pieces to begin with. Okay. So, write a function represent, okay, so the amount of candy left. All right. So A equals, I'm saying A for amount. So the amount of candy left. If we begin with 100, so we have an initial amount of 100, and then what's happening to that 100 pieces of candy? Well, we're getting 3 each time. So are we adding to the 100? Taking away? So if we have 100 and grandma's giving us 3 pieces, the jar is going to have less and less candy. So we are going to subtract the 3 pieces of candy each trip. So minus 3C for 3 pieces of candy, but it's 3 pieces per visit. So I think it should be 3V because it's minus 3 pieces per visit. That makes more sense. So independent and dependent. Does the amount left depend on the number of visits, or does the number of visits depend on the amount left? I think we were right the first time. Amount depends on the number of visits. So that becomes our independent. So when we're writing in function notation, A of what? The amount of, well, visits tells us how much candy we have left. So 100 minus 3V, 3 per visit. So that's literally the only difference between an equation and function notation. It's just that little piece how we write it in the beginning. That's the only difference. Okay. So again, go back up, function or not. Is this relation a function or not? Go back up. What is a function? A set of ordered pairs. No problemo. Key part. Each x has exactly 1 y. Okay. So each x has exactly 1 y. So we're going to use a mapping diagram to determine whether these relations are functions. So in our mapping diagram, our inputs are on the left, so my x's go on the left, and my outputs or my y's go on the right. Now this is really important. If any values repeat, we only write them once. If you write them more than once, then the mapping diagram won't work to show you if each of these x's has only 1 y. So let's go ahead. I'm going to try and keep it in numerical order, so least to greatest. So my x values, I've got a 1. Okay, what's the next smallest? 6, 4, a 3. I've got another 1, but I already wrote 1, so I don't need to write it again. Remember, if they repeat, only write them once. We have a 4 and a 6. Okay, so there's all my x's, my inputs. So now let's look at our outputs, our y values. 2, 8, 7, 9, 3. Okay, so the smallest is 2, then 3, 7, 8, and 9. Okay, so to use a mapping diagram, we're going to map what inputs go with the outputs. So 1, 2. So 1 goes to 2. Cool. 6, 8. So 6 goes to 8. Yep, literally that's all we're doing. This is a mapping diagram. 4, 7. 4 goes to 7. 3, 9. 3 comes all the way down to 9, and 1, 3. 1, 3. So we have now mapped each input with its corresponding output. So we want to know, does each x have exactly one y? No. Look at 1. It has 2 different outputs. So since the x's repeat, we have a 1, 2, and a 1, 3, this is not a function. Each x does not only have one y, 1 repeats. So you might want to write yourself a little note. X's can repeat, y's can repeat, x's cannot. Okay, if x's repeat, then that input is going to have more than one output. All right, go ahead and pause the video and set up this next mapping diagram. Try it yourself. All right, so I have my x's on the left, y's on the right. Fill in all my inputs. 1, 2, 3, 4. Well, that was nice. That went in order. And our outputs. 4, 5, 4, 7. So 4s, I only write them once. 5 and 7. And now let's map. 1 goes to 4. 2 goes to 5. 3 goes to 4. And 4 goes to 7. So does each input have only one output? 1, yes. 2, yes. 3, yes. 4, yes. So this one is a function. Each x has just one y. Now look, this y repeats, but that's okay, because if we were to graph this, it would pass the vertical line test, and I'm going to show you that later. But the y is allowed to repeat because each x only goes to one y. So y's can go to 2 x's, that's fine, that's not the issue. Each input has to have its own output. That's what's key. Okay. I will see you back here tomorrow.